All right, so today we're starting Chapter 8, Section 1. It's called Inverse Variation. This is companion to direct variation, which we did a few chapters before. So our learning objective is to recognize and use inverse variation and to use joint and other variations. Okay, essential understanding now. Make sure you're writing down only the stuff that I highlight. So it's important that we highlight direct variation. That was y equals k times x, where k was that constant. That's direct variation. Inverse variation is xy equals k, or y equals k over x, or x equals k over y, as long as k is not equal to 0. When two quantities vary inversely, as one quantity increases, so one increases, the other decreases proportionally. For both inverse and direct variation, k is the constant of variation. This has already been a vocab word for us. So k is that constant of variation. You may be asked to find the constant of variation, so a little bit important to know that terminology. All right, so if you look at this B1 right here, we're going to multiply the 0.2 by 40 and get 8. 0.5 times 16 and get 8. 1 times 8 is 8, and 2 times 4 is 8. Because when I multiply x and y together and get a constant, this is an inverse variation. Let's test C. Does that work for C? 40 times 0.5. I actually know that one. It's 20. 1.2 times 12. Well, 12 times 12 times 1 is 12, and then
14 plus 6.
2. So like 12. 14.4.
14 times.
I guess it's
16 times 16.8.
16.8. Are you sure? 12 times 1.2?
Oh shoot, it's 12.
12 times 1.2?
14.4.
Oh, 14.4. 10 times 2 is 20, and 6 times 2.5 is 15. So this is not inverse variation, and then we're going to test for direct variation, correct variation. So that happens when we go y divided by x, and we can do that real quick with a calculator, Chad. So 40 divided by 0.5, that's 80. 12 divided by 1.2 is 10. 10 divided by 2 is 5, and 6 divided by 2.5 is 2.4. So this guy is definitely neither. All right, what is 8 divided by 0.2? So that we're testing for inverse variation. What's 20 times 0.5? Sorry, 20 divided. Oh, let's do inverse first, and then we'll test for direct. 8 divided by, 8 times 0.2. And 20 times 0.5. 16, and 40 times 1, I know that one without a calculator. and 60 times 1.5, 90. So this is a not inverse, because my k isn't the same each time. So let's test for k. Let's test for a direct, which is y divided by x. So that would be 8 divided by 0.2, 40. And 20 divided by 0.5. Okay, and 40 divided by 1, I can do that. And 60 divided by 1.5. Okay, so now that we have what each one of these guys is, so this is direct, this is inverse. We're going to make a little equation, right? Function models for the direct and inverse variations. So we're going to say f of x is equal to r for direct y equals k times x. So we can say our k is 40 times x. Inverse variation says y equals our k divided by x. So our k here is 8 divided by x. Okay. Suppose x and y vary inversely and x is equal to 8 when y is equal to -7. What is the function that models the inverse variation? What does the graph of this function look like? And what is y when x is equal to 2? So the first thing we do is write the general form for inverse variation, and that is y equals k over x. Substitute for x and y. -7 equals k over 8. Solve for k. K equals -7 times 8, or -56. So the answer is y equals -56 over x. What does the graph of the function look like? Well, let's go ahead and graph it and take a snippy of it and put it here. All right, so you're going to sketch this graph here. It has an asymptote at x equals 0 because that will make your entire denominator 0, and we know we're not allowed to have a 0 denominator. So it starts down here at like -50, comes and does a little loopy up to the y-axis, and then it catches itself back down here, -50, and gets really close to the x-axis, but never really touches it because x can't equal 0. Right, and then at the last part, what is y when x is equal to 2? So y equals -56 divided by 2, and that would be -20. After a major storm, your class volunteers to remove debris from yards. The table shows the time t in minutes that it takes a group of n students to remove the debris from an average-sized yard. It's debris, but it says minutes. What function models the time needed to clear the debris from an average-sized yard relative to the number of students who do the work? And how many students should there be to clear debris from an average-sized yard in at most 25 minutes? So what I'm going to do is create a little table and see if this fits an inverse model. We look at the data. The more students who help, the less time it takes to clean up. So an inverse variation seems appropriate. If this is an inverse variation, then NT equals K So when we multiply the number of students times the time, it should get a consistent answer. All right, so when we graph it, we get kind of an inverse situation. So let's go ahead and take our data table. What we're going to do is we're going to multiply X and Y and find and see if I get a K value. That is, it's not, because it's data, it's not going to be exactly. You know, you're always going to have that one kid that's standing there picking flowers instead of picking up trash. So it's not going to be exactly, but we can find our K pretty quick. 1 times 225 is 225. 75 times 3 is 225. 45 times 5, my calculator is not serving me well today, is 225. And 14 times 16, not 225, but close to 224. So because our K values are, if you were doing this in a graphing calculator, this would be list 1, list 2, and this would be list 3, which is list 1 times list 2. So L1 times L2 is almost always 225. So this is going to be, we're going to be able to use an inverse model. So what function models the time needed to clear the debris from an average sized yard relative to the number of students who do the work? So if we go time is equal to 225 divided by n, because we found our K is almost always 225. How many students should there be to clear debris from an average sized yard in at most 25 minutes? So if we want our time to be 25 minutes, I can solve this by multiplying both sides by n and dividing by 25. I'm going to go ahead and do that. I get 25n equals 225, and then divide both sides by 25. 225 divided by 25 is 9. So to get it all done in 25 minutes, you need to have 9 students. The last part of this section, we're going to talk about combined variation. So not only do we have a number of items being multiplied, but now some of them are multiplied, some of them are divided. So we have to look at the way they're presenting the information and decide if it decide which equation goes with how the information is being presented. So when one quantity varies with respect to 2 or more quantities, you have a combined variation. When one quantity varies directly with 2 or more quantities, you have a joint variation. So the difference between joint and combined, one quantity varies with respect to, and one quantity varies directly. The volume of a cone varies jointly with the area of the base and the height of the cone. E equals K times area of the base times the height. All right, so if you vary jointly with X and Y, you're equal to K times X times Y. If you vary jointly with x and y and inversely with w, then you got kxy over w. If you vary directly with x and inversely with the products of wy, then you're equal to kx divided by wy. Let's see how we can put that information together in a meaningful way. The number of bags of mulch you need to cover a planting area varies jointly with the area to be mulched, A, in square feet, and the depth of the mulch, D, in feet. So the number of bags of mulch varies jointly with the area to be mulched, A, in square feet, and the depth of the mulch, B, in feet. So B is bags. And this is what my students fail to do on their portfolio assignments, is defining their variables. They throw out the equation but don't tell me what each of those pieces mean and why they're putting them in the places they're putting them. So make sure you define your variables. Area to be mulched, and D is depth of mulch. And what's K? Since I have a K in there too. Not Kelvin, because it's lowercase k. See how that would be confusing? That is the constant of variation. And we always have to solve for that. All right, so then they're going to give you information so you can find your K. And then they're going to have you put it together and use your equation to find the amount of bags. So this is thankfully a predictable process. Find the constant of variation, use the formula. Super, super predictable. So if we need 10 bags, so B is 10, K is K, we don't know what that is, we're solving for that. To mulch 120 square feet to a depth of 3 inches, unfortunately, we don't want a depth in inches, we want a depth in feet. So we can't just use 3. So 3 inches is how many feet? It is not 36 feet. 3 inches for every 12 feet. So 3/12 is the same as 1/4, or if you put in your calculator, it's 45. All right, so we got 10 equals K times 120 times 1/4 feet, and I get 10 equals 1/4 of 120 is 30. I divide both sides by 30, and I get my constant of variation is 1/3. So now I have my K. I can come back here and make my equation. Number of bags I need is equal to 1/3 A times D. A is area, D is depth. So now I can find how many bags I need if I have 200 feet and a depth of 4 inches. So bags of mulch is 1/3. I got 200 square feet, and I have 4/12 foot depth. So let's clean this up a little bit. 4 over 12 is the same as 1/3. 1/3 times 1/3 is 1/9. 200 divided by 9. 22.22. So that means I need 23 bags. Unfortunately, they will not let you rip off a 0.2 bags of mulch at the store and just buy that 0.22. Unfortunately, we have to buy the whole bag. So that's 23 bags.